Hi everyone, I am Mohammad Akhtar Munir from MBZUAI. This work, GeoBench-VLM, is a collaboration with IBM and ServiceNow, and it is accepted at ICCV 2025 as highlight. We introduce a benchmark that tests how vision language models actually handle geospatial problems, spatial grounding, counting, temporal change, and multi-sensor data. Earth observation needs precise answers. Where, how many, and what changed before versus after. In these images, objects are small and scenes are dense, and the imagery comes from multiple sensors RGB, SAR, multispectral. So many VLMs miscount, mislocate, and ignore time. On the left image, the true count is 86, yet several models answer 69 or 103. On the right image, models miss tsunami or even don't follow the instructions. GeoBench-VLM exposes these gaps with objective scoring so the community can fix them. GeoBench-VLM spans 8 categories and 31 tasks. You can see them in the sunburst on the right. We built 10,000 plus human verified instructions, so scores are trustworthy and we evaluate 13 VLMs both open and closed. The tasks cover the full spectrum: scene and object understanding, counting, spatial relations, referring detection and segmentation for grounding, temporal understanding with pre-post images, non-optical questions using SAR or multispectral, and captioning. This breadth lets us measure semantics, spatial precision, and time awareness in one place. Here are the tasks we benchmark. Event detection: identify the disaster. Scene understanding: name the facility or land use. Temporal understanding: count damaged buildings from pre-post. And non-optical: estimate earthquake magnitude from SAR cues. On the left column, you can see the object classification. Fine-grained ship types, image captioning, rich but concise descriptions that mention spatial layout. On the right column, there is object localization and counting. Here a spatial relation MCQ forces true grounding and segmentation where models must output a mask, for example, roads. Most are MCQs for objective scoring, counting using realistic distractors, and grounding tasks require the correct box or mask. We start by sourcing open Earth observation data and selecting scenes that cover the full spectrum, urban and rural, coast and inland, disasters, ships and airfields, and vegetations. So models see the variety they will face in practice. We then incorporate multiple modalities as provided by each source, RGB, SAR, and multispectral, keeping their native format so characteristics are preserved. So first we annotate and derive supervision. We manually label spatial relations, generate referring boxes, and convert available semantic masks into binary masks. We also attach metadata like counts and classes. Second, we pair temporally pre and post images of the same footprint to build bi and multi-temporal items for the change and damage questions. Next, we generate prompts and options with strict rules. Tasks are cast as MCQs. For counting, we add 20% and 40% distractors to avoid guesswork. We create paraphrases to test prompt sensitivity, and captions are concise but include special cues, so models must ground descriptions. Then we run QA and splits, human verification, deduplication, and leakage checks. And we balance by task type, scene density, and difficulty. That keeps evaluation objective, fair, and reproducible. On the MCQ, Lava 1 Vision ranks first at 41.7, which is only about 2 times the random performance. So there is a lot of headroom. Across tasks, semantic classification is relatively stronger, while counting and spatial relationship columns stay lighter for almost every model. We also see model specialization. GPT-4o and Qwen2VL spike on few semantic tasks. EarthDial is comparatively better where Earth observation priors matter, but no model is uniformly good. On the temporal geospatial side, we see clear specialization. EarthDial leads in crop classification, farm pond change, and land use, the places where Earth observation priors help. GPT-4o takes damage building count and disaster classification, showing stronger high-level semantics but not consistent Earth observation specialization. On referring inspection detection, Sphinx tops and Earth dial is second. The jump from IUU zero point 0.5 to zero point 0.25 means coarse grounding is often okay, precise boxes are still hard. Several general VLMs trail, suggesting format handling and grounding gaps. On the regression side, Lava 1 Vision has the lowest aggregate error. The next band is GPT-4o, RS Lava, and Earth dial around 70 to 74. At the other end, Ferret, Spinix, and GeoChat accumulate the highest errors. On the right, we test 5 prompts per item. The largest variance appears on counting tasks. GeoBench-VLM makes the blind spots visible. The hardest areas are spatial grounding, temporal understanding, and other fine-grained geospatial skills, especially counting and precise localization. We are releasing a benchmark that gives objective, reproducible measurements so the community can track real improvements. Thank you for listening. The QR has the paper, code, and the benchmark.